Our next speaker is Natalie Somersall. The title of her talk is Whodunnit, a Git repo mystery. Please welcome Natalie.
I hate to say everyone was wrong here, but hi, my name's Taylor, and I was born in 1989. Except that's only true in GitHub. And on that terrible disappointment for everyone here, let's learn about what you can reliably know about who did what and when in a Git repo. Hi, I'm actually Natalie. These are my social accounts. More importantly, all the slides will be here probably next week. I do AppSec and software factory stuff, well, what's now called software factory, with feds and defense industrial folks. So that's all the commercial sector that really supports our direct federal users. So NIST, ITAR, CMMC, FedRAMP, all those fun things. It's kind of where I live day in and day out. And because of that, I have been in the hot seat more than once, and I've walked a lot of people in that hot seat, way more than once, through code audits and really hard questions about what we can prove that we know in a code base. Oh snap, what's a code audit? So normally when I open up these conversations, a lot of people are like, well, Git does version control tracking, duh, that's what it does. It gets a little harder once we start adding more things here, like, oh, my infrastructure is code. How do I prove these changes? We had an incident. Were leaked secrets to blame? Or more importantly, did these attackers compromise our code? Did they make changes? How can we know and tell this? We're making an acquisition. Can you even purchase the software? What does that due diligence process look like? You work with foreign nationals. On some contracts and some programs, being affiliated with a foreign government in any way, shape, or form, you need to at least be upfront with that. So what code are these people changing and when? Our software factory must carry some sort of compliance certification, or this software is in scope for Sarbanes-Oxley. So if you're starting to talk about public finance, your publicly traded finance, life gets a little hard. And some of these audits can be self-attested, some can be third party. So you're trying to explain things that happened a year, 2 years, 3 years ago. When you joined the company 6 months ago, everyone who was there left. What can you know? So talk a little bit about where we're going today, and I definitely had way too much fun with mermaid diagrams. The process that we're looking at is human being changing files that are then stored in a Git repository on a local machine, an endpoint or a developer workstation, and then pushing those into some sort of central remote. So GitHub, GitLab, Bitbucket, Azure DevOps, any of those central remotes. We're going to talk a little bit about biases and threat model because that really changes how we think through these questions. Who, what, when, where, why. So we're going to go to journalism school today. And then talk a little bit about what we can do about this and really why this is even important to begin with. So I have some biases. I have been working with Git for a very, very long time. Git is hard. I feel like it's better than literally anything else. And maybe a lot of that is inertia, and maybe a lot of that's just because it's genuinely great. And most developers, in my experience, do not interact with Git from the command line, and you shouldn't have to. You shouldn't have to memorize a couple of shell commands just to make some changes to code. Another bias I have is identity and authorization is really, really, really hard. There's a reason that you can spend an entire career in just identity management or just authorization or authentication. It's because it's complicated and difficult. And my last kind of maybe spicy take here is that auditors are humans too. We're spending a little bit of time here at the intersection of several multi-billion-dollar industries: identity and authorization, endpoint management, regulatory compliance, developer tooling. All tons and tons and tons of complexity here. So that's where we're at. Lastly, for threat model assumptions, I am not going to talk a lot about state actors. When you have an adversary with infinite number of time and money and manpowers, that is a whole different threat model than what we're going to end up with today. And we're going to talk a little bit about like, hey, no bad code goes in and no good code leaves, but we're not really going to talk about intellectual property law or malware detection or any of that. We're really going to focus on, but can you prove it? So with that, let's talk about that magical directory .git. So when you clone a repository or initialize a repository, a directory gets created in that project called .git. What goes on in here? Distributed is here to stay. So this is the key point that we're going to have a hard time with Git and really, really love about Git. Before a distributed version control system, I started my career spending way too much time unlocking files in a system called Visual Source Safe. So I have a sticker that says social coding on here because anti-social coding did exist, and that was when your team lead took a vacation and didn't unlock his files beforehand. This easy conflict resolution gave us all sorts of really cool stuff, but on an audit perspective, it adds some difficult conversations. Everyone has their own copy of everything locally on their endpoints. And where they work and propose those changes are on their endpoints. And there's always that one person in an audit who is like, no, my users took cybersecurity training. They would never click a phishing email. They would never do anything silly. It does happen. But keep in mind that all of this audit is about a user on an endpoint. So they are responsible for who they say they are. They're responsible for all of the content configuration, so storing binaries, adding secrets, ignoring files. All of that happens where that code is actually getting changed. And local execution of code. So you have a concept in Git called hooks, where at certain points in a developer lifecycle, so you pre-commit or post-push, these scripts can run. And that can also add a little bit more complexity. And then our endpoint, you can sign commits that we're adding cryptography in those signatures on changes. Again, one more endpoint control. So this .git directory is full of magic. And I put some stars next to what most auditors I've interacted with are going to highlight. And that's the config file, the hooks directory, and the logs directory. And I'm going to say rightly or not, because some of these things don't really tell you what you really want to know. Because the first thing to understand about Git is that the order of resolution of these configurations is friendly to local and hard to audit. So local configurations take precedence over global configurations, take precedent over system configurations. So that's great that you have all of your Windows endpoints and whatever SCCM is called these days. However, that system-wide configuration can then be overridden by a developer's local profile or be overridden again by a particular project. So if I'm working on one project, I can have settings specifically to that. So setting anything at git config is really just a suggestion. It's not a mandate. Additionally, none of these files are version controlled by your repository. What is really handy, though, is that at least locally on that endpoint, you can pretty easily tell what scope is setting each setting. So if you use git config and you show that scope and you show that list, you can see, hey, this is set globally, this is set locally, this is set by a system. So at least you understand where those scopes are set. And everyone likes to talk about this logs directory because clearly when you're going through an audit, you see logs and you're like, oh, hey, logs, that's what we need. But it's not logs in the sense of this is going to prove that Natalie changed this code. It's logs in the sense of these are the commits that have happened and what order they play in. So highlighted a couple things here that are a little important. Your local state. Each branch has their own folder here as well. And then if you have multiple remotes, each of those can be tracked separately as well. So again, these logs are a little disappointing. We have a SHA for the parent, so that's the change that we're coming from. We have our current commit SHA. We have who, reportedly, when, reportedly, as detected on the endpoint. And we have the commit message, which hopefully gives us what happened. But again, none of that tells us what changed in that log. So having resigned to the fate of working for these answers, now we need to figure out who even wrote this code. This is the money slide right here. And that is the most difficult conversation that I have had with people moving to Git, with projects moving to Git, with trying to audit code in Git, is that there's almost always two identities, and they are not reliably linked. Or how you want to link those two identities is up to you, I think is a better way to put that. So there's who you say you are, and there's also who you say you are to that Git remote. So Git thinks you are who you say you are. It cannot create a commit without a name and an email address to use. And this little bit of friction is so well known that the platforms for remote repo hosting, in this case, I think this is GitLab, will prompt you up front. If you click the button that says create a new repository, this is how you set your name and this is how you set your email. All of them do this, because you can't even create a commit without setting this info. But who do you say you are? As an example, on this laptop, my global settings are my work identity. This is my work issued laptop. And all of my work identity, my email, my key signing, all of that is set up for committing to ChainGuard's intellectual property. However, I also am a human being. I code for fun. I have my own open source contributions. And locally, not globally, I will set up those projects to use my personal email and my personal SSH key for commit signing. And those commands, all they do is edit a text file. They edit that git config file in whatever scope that we set up earlier. And you can also edit it with Vim, Emacs sed, open it in VS Code. Like, no one cares. It's just a text file. As an example, I'm gonna look at this this lovely screenshot here. So I just added some wheres. And I did all the fun things here where I said, hey, I'm just a maintainer. I misspelled Gmail. All of the things that should set up red flags, all I did was like add white space to a text file. But I can then go back and say, hey, this commit was attributed to maintainer at the misspelled Gmail domain. And if I go through git log and say, hey, show me all the commits with this author, I can see that allegedly, again, at this time, I added some wheres at June 10th. So I pushed that code, and I think in this case, this is GitHub, and it shows up as verified. Remember how we said that there were two boxes of identity, one on Git and another on your remote? In this case, you can see maintainer is listed as the author of the commit, but some Natalie pushed to this remote with credentials belonging to that account. And more importantly, that code was signed by some Natalie's signature. So who is responsible for this code? Does it matter that you are who you say you are when you control that identity elsewhere? So somewhere between distributed and centralized is where a lot of companies end up. And one of these models is much, much easier to audit in some ways than another. So how do we bridge that gap? Because Git is both distributed and bring your own identity, but all of these audit controls are really around centralized account management, centralized identity, centralized cryptography. So we have an identity provider that is interacting with that remote with SCIM or SAML normally, and that is your well-respected boundary. And then what's happening on the endpoint, I don't want to say is the wild, wild west, but it can be the wild, wild west. Because now we need to prove it. So what we can do now is say, we know that this account committed these changes. So even if they didn't author it, they did push it to this remote. And that her self-supplied key signed this commit. So the key that I generated or somebody generated has been added to this account. So it's a second factor, but it's not necessarily a second factor that, to go back a slide, comes from your identity provider. Again, it's a user adding that key to their account in the remote. So even if they were authored by someone else, I would normally argue that, hey, this account is either compromised and we have a problem elsewhere, or that this account is responsible for pushing this code. So in minimizing the ways that it can go wrong, I will never not preach the gospel of SCIM. So the ability for your identity provider to provision accounts in, I would say, child services. So your identity provider would be your central point of authority for your email, for your VPN, for your endpoint provisioning, but also for things like your account, your chat for Slack, your chat for GitHub, or your code for GitHub, et cetera. And if you can't do that, single sign-on. Yeah, is there a question? Yes, system for cross-domain identity management. So it is a protocol that came out in, oh goodness, I'm gonna mess this up because it's recorded, of course. But it came out a couple years ago, 2016, 2018, somewhere around that time frame. And it's been very, very popular in enterprise software, specifically for this use case. So the idea is that when a new user joins your company or rolls onto your contract, that you add Bob to a group. And because Bob is now a developer on this project, he'll get access to these files in SharePoint. He'll get access to these 4 entitlements in Google or in these, Canva, Slack, GitHub, whatever your enterprise stack is. But it provides the ability then when Bob rolls off that all of those accounts belong to you and you can deprovision them. So you can lock them out. The account belongs to you. And you can automate that lifecycle management a lot easier. So it's an open standard. Failing that, single sign-on, again, gives you that single point of control of, hey, if we need to sign into Okta in order to access whatever, like that will still provide you that ability to say, hey, when this person rolls off, their account might still be theirs. However, they can no longer access these resources. It is 2024. I can't believe I'm still having this conversation, but I am. Please reduce the use of long-lived credentials anywhere they're ever stored in plain text. This is passwords, this is API tokens, but this is also SSH private keys. So again, we're talking about a lot of that intersection with endpoint management, which is its own multi-billion-dollar industry. And then requiring signed commits doesn't do what you think it does. About half the time I have this conversation, we require all of our developers to sign commits. And that clearly always and completely airtight proves that Natalie wrote this code. As we'll start to see, it really doesn't do what you think it does. So let's talk about that a little bit. So there's 3 common methods of commit signing: GPG, SMIME, and SSH. So SSH was a recent addition. So SSH keys, all reasonably familiar. It's public-private key pair. That private key, according to your SSH daemon, needs to be locked down on the file system a little bit. but that's still a plain text private key on an endpoint. You can store it on a YubiKey like mine, or if I was about to touch it and then realized if I touched the YubiKey, it would blow up the text. That's how ingrained. Oh, YubiKey. Let me just touch. Yeah, I'm well trained. So you can store those private keys elsewhere, and you should. CAC is a common access card. So if you've ever been issued a identity card with a little PIV chip on it, and that chip hosts a certificate, you can store keys on there as well. Normally that's GPG keys. And SMIME is the cryptography system most commonly used for email, and genuinely nothing else. I have not personally run into SMIME commit signing at all. But think of it more as a tamper-resistant seal on a specific set of changes, not a link to identity. And there's some problems with this. So every end user on every endpoint that's committing code needs to configure commit signing. So when you sign a commit, you're using the -S every single time you commit. This is a little bit of a problem sometimes. You also need to normally self-host your Git server for custom certificate authorities. So if you're using a SaaS product, it's typically unreasonable to ask GitLab or GitHub or bitbucket.com to say, hey, I need you to trust my super special certificate authority that I have rolled myself for all of my users. Not really going to fly, because then you're going to have 800 different people with way too many certificates to manage performance-wise. So again, you're going to need to self-host your commit or your Git server for custom CAs. You need to verify commits. So having a signature is no good if you can't verify the validity of that signature. And it's not possible in some platforms to reject unsigned or untrusted commits. So again, conditions apply because every platform and every version of that platform has their own rules and conditions around that. But most importantly, secure random key generation is really hard. And it's really, really, really hard at scale. So again, we're adding more and more complexity to this system. And note again that each regulatory kind of compliance box has controls around aspects of key life cycle. What cipher strength are you using? What randomness are you using? What algorithms are you using? So again, this is just adding more and more and more for you to prove. And again, these all rely on long-lived private keys. The last thing I'll kind of mention here is, are you who you say you are? So in this case, I clicked the little unverified pillbox and it says, hey, you need to verify your email address to verify this signature. And verified just means that the particular key used to sign that commit is also part of that user account's email address. So it's trying to link that who in Git to that who in that remote repository. So making sure that, in this case, somenatalie@github.com is actually owned by somenatalie. It's not actually a part of Git, but it is a very, very handy feature on specifically public remotes. Because here's what that means. It means that one single human or organization controls both that email and the account. So if somebody tried to send me an email to my github.com account, it would bounce. That I don't work there anymore. However, I still have that email on my account. Adding those old emails back as unverified means that I retain that commit history for all of the commits to that email, but more importantly, also prevents name squatting on those old email addresses. And one more point is it only verifies that the key that signed that commit was verified or not at the particular time. So I genuinely did work at GitHub when those commits were made. And if I had taken this screenshot during that time, those would all be a straight line of green verified. So again, this is where time and time matters here. And then there was a very, very common supply chain attack lately around Dependabot PRs, because you are who you say you are. Some malicious actors said they were Dependabot and opened, commits and pull requests that looked like Dependabot but were not signed. If you click that little green button, it will always, always, always be signed by a signature that is owned and operated by github.com. So disappointed in our shifting identity, we now need to figure out what even changed. So in this case, what changed is what files actually changed. And I'm a huge believer in using things for what they're meant for, because that makes our audits a lot simpler. Tracking what changed is exactly what Git does, and it does this phenomenally well. So I've made some assumptions here that we're all familiar with the basics of, committing a set of changes in Git. So we can spend an hour just talking about like, this is what Git is, this is what it does, but we don't have that type of time. But let's talk about making some of the harder questions I've come across a little easier. So there's some nifty tricks, some hidden foot guns, and one extremely shameful use of sed. First is diffs and patches. So you can use Git without any central remote repository at all. Git existed before there was a GitLab, a GitHub, a Bitbucket, a Azure DevOps, kind of, sort of. So Git is its own thing. And there are a lot of places that use what's called a patch-based workflow. So Git itself is not developed on GitHub. The Linux kernel is another really good example of that, and I believe Postgres as well. So they work by emailing patches around. And these patches and diffs are not the same, but they do carry that similar set of changes. So we've been talking a lot about the beautiful GUIs that can be built on top of your set of changes. However, those aren't necessary for Git to work. Patches are diffs that carry that, again, very self-attested or easily manipulated metadata on top of the file. So you can see that this is, from, that's that parent. You can see a completely meaningless date. But you can see apparently some Natalie at chainguard.dev did do something on Tuesday, April 23rd, and made a fabulous commit message. And everything below what's shown here is a regular diff. But you can see if you were, reviewing this code manually, that you could say, oh, hey, these are the files that changed. We created some files, we deleted some files. And if you are interacting with Git at the command line, it's format patch to create it and AM to apply it. But a diff does exactly what you think. So if you're familiar with any of those visual diffing tools, this is what goes in and out of those. And it just gives you that plain text diff. And in this case, this is a new file, and you can tell that in a couple of ways. The first way you can tell that is the parent commit is all zeros. So all zeros means nothingness. And I added this commit was made from the web while logged in. And the nice thing about these is that these centralized platforms make interacting with these pretty easy. So if you click on any commit in GitLab or GitHub, you add .diff or .patch at the end of that URL, and you will get a plain text formatted to your browser, to your API client, whatever you're ending up using, of exactly that. So you can build a ton of things on top of diffs and patches if you need them. You can interact with them with curl or an API, all that good stuff. And there's a ton of shell wizardry that you can perform here as well. So this is one of my favorites. It is taking git log, it is sorting it, giving me only the unique entries, and then giving me the top 5 changes. So in this repository, I know that these are the 5 files that change the most. So if you're starting to try and figure out like, hey, what do I even need to pay extra close attention to, or what would be an anomaly? That's one more way to do that. And everyone has some level of shell wizardry that they have done on Git log. Because here is that absolutely shameful use of sed. About every other code audit I've gone through, at some point someone says, okay, look, this is fabulous. I'm glad that you have this lovely web UI. What I really want is a spreadsheet of changes. I need to know who signed on things, and I don't have the time to go through and click the 10 different pages in GitHub to go back in time on the history of the commits. So here is that shameful use. It outputs the URL of that commit for easy viewing if you want to open that in GitHub or GitLab. But it gives you the commit ID, the author, the signature status, and name of the signer, and just number of files changed and number of lines changed, which I feel deep shame that I had to do this for an audit. But everyone has a hill they'll die on. And wanting a spreadsheet of changes of who changed what is not the hill I will die on. However, all of that data does exist in Git log. Like all you're doing is piping Git log through a bunch of uses of sed. The other foot gun I see quite frequently is the use of Git LFS. There is a general rule around Git repos, and that is that if you cannot diff it in plain text, don't put it in your repository. Don't put finished binaries in your repository. Don't put DLLs in your repository. In this case, don't put a Photoshop file in your repo. Git is very, very good at diffing text, and Git is actually really bad at handling large binary files. But again, in practice, I feel like no one really follows this. So there's this really cool addition called Git LFS. So it's a set of extensions on top of Git, and it uses pointers to point at that big file in the repo. And this gets really, really scary every time I talk about it with auditors, because they're like, pointers? Pointers? That means that we're not tracking what's actually changed, we're just tracking a pointer. That's terrifying. And then I talk to team leads and they're like, but we have all of this stuff in our repo already. We can't move it to another system. And then there's that extra step of using Git LFS that can be some friction on the developer side as well. And it doesn't always have to be this way. So Git LFS is defined in an attributes file, so you can version control that file in a repo to say, hey, everyone adding Photoshop files to this repo, add them using Git LFS. And then it uses a filter called clean and smudge to perform those interceptions. So as you're trying to commit files, it will go ahead and smudge them. So that goes from the staging directory to like, hey, I'm actually going to commit this file. That's the curved arrow on this diagram. And then the clean goes from working to staging. So it's that straight vertical arrow. So it looks to you on your local endpoint that you are interacting with the real big file, because you really are. You brought down that big file. However, once you start to change it, to start to think about putting it in a remote, it's actually going to go to a separate file store, and there will be a pointer to that. And that means talking through this gets super duper gross, because things I've really been asked, I need to perform a full AV scan of this file. I need to be able to intercept files and quarantine them. I need to be able to understand what's changed on this particular file system. And for the most part, this can't happen quickly enough for the Git remote to accept or reject that commit, because there's a very, I think it's 10 seconds, short amount of time before that accept or reject decision has to be made. And this can also break self-hosted stuff. But more importantly, these pointers are actually designed in a way that makes auditing very, very easy. So here's an actual real text example of a pointer. I just shamelessly stole this from Git LFS's documentation, but it gives you the version of Git LFS that's used. It gives you the object identifier, so the SHA-SUM, and the size, which means that if the threat model here is, I need to know if somebody has changed this large file system, either on that remote that they have access to or on my endpoint, it is beyond mathematically unlikely that two objects will share a SHA-256 sum. So that's 1.16 times 10 to the 77th power, or many, many, many times more than there are grains of sand on Earth or drops of water in the ocean. So additionally, they also have to share the same size, the exact same size. So having these untracked changes as a possibility is very, very unlikely. Or, the easier option here is you can just use something that was designed for binary storage. Like there are entire suites of products designed for storing your NPM packages, storing your containers, storing your Photoshop files, et cetera. Getting users to use LFS, in my experience, has been far more of a problem than any security implementation. And CVEs around Git LFS tend to be around remote code execution or resource exhaustion, which are not, tracking or untracking changes. Lastly, I am once again asking you to please, for the love of all that is good in this world, stop putting secrets in repos. I'm just a girl asking you, stop doing this. Because when we start talking about secrets and repos, the very next discussion that I have is, well, how do I fix this? And there's a whole industry on detecting and as we heard earlier, you're figuring out what to do about that proactively. But I'm coming in more in a reactive fashion. So how do you remove a secret from a repository? You can't. Because once that secret has been pushed to GitHub, GitLab, even if it's private, you have lost control of that secret. Because now, let's say if everyone in this room has access to the same repository, I do not know where that code has gone from that remote. And even if I do, I don't know the second or third places that has gone once it's left the central and now it's on somebody's endpoint. What this means in practice, unfortunately, is force pushing changes. So you are rewriting history, big, giant, ugly red audit flag, and then you are force pushing that revised history to your remote. Figuring, oh, hey, well, GitHub's not complaining about a leaked secret there anymore, so obviously we're done, and no one has ever seen that secret. It was never leaked. It was never compromised. That's not what happens. So what happens is these what we call tip-only migrations, or that force push of we removed and rewrote the history of that code base. It's also used to remove large files from a repo. So rather than saying, don't ever force push, because I am going to tell you that, I'm going to tell you, please just own the fact that you screwed up, you committed your AWS key, you're going to rotate it, and you're going to learn from this. That's not always what happens. But living with force pushes means a couple of things. It means first, be obvious. And once you're obvious, make it even more obvious. Like, hey, this is a force push to do something. See, an external issue tracker for more details. So, if we had an incident, say, hey, please see this ServiceNow incident, or please see this, Jira discussion, whatever that system is for you, be obvious. And if it's removing large files from for an LFS migration, so if you have that large file, it'll be committed multiple times at each change. So you're rewriting quite a significant portion of history. Only do that one thing in that commit, and then consider using a file called git blame ignore revisions to quiet down git blame to a reasonable amount. And what this means in practice is if you're relying on the ability to use git blame to look and see, hey, Natalie changed this chunk of code in this file 3 months ago, and then her team lead went ahead and changed this other block of code 2 weeks ago. Having these really, really noisy commits where 1,000 files were touched gets to be kind of gross. And then if you're using a central remote, block force pushing universally. So block it at that enterprise-wide level scope, and have those logs sent to your SIEM so that if you are doing this, you have an incident response person in the loop who has the ability to unblock this, which might force number one there of having that incident, reasonably well tracked. And it's going to set off all sorts of alarms in your security event system to say, hey, Natalie unblocked force pushes, and there was a force push to this repo at this time. It's not to say that it's always wrong to redo history, but it's definitely going to make these conversations a lot harder. And then I put 2 projects there for if you're self-hosting, for trying to detect force pushes as well. But that's controlled, again, entirely on the remote. So armed with some wisdom here of what's changed, now we have to figure out when. When is really fun because all of that time is completely self-reported. So I can use git commit and then add a flag there to say it is 3 weeks ago, a year ago, 10 years ago, whatever time that I want to put in there. Because you can just set it to whatever you want. And this means your GitHub contribution graph isn't actually proof of anything. And it's also remarkably useful for randomly seeding those honey tokens from earlier in the day backwards through time, or at least they look like they're backwards in time. Random date distribution with meaningful commits makes it a lot less obvious that this is not really valuable. And without any intervention, commits default to now whenever now is on your endpoint. And I'm not going to make any joke about network time drift, but it is a thing that we all live with, and we're all very sad. Git log also has a since and until date. So if you need to scope searches within that repository, that's been phenomenally helpful to me many, many times over. And again, what files changed most often? So using that date filter here, you can get the most frequent within that date window. Again, tons and tons of products exist in the developer experience and statistics and DORA metrics type tool space, but this data does exist in Git. So now that we understand and are enlightened by that meaninglessness of time, let's figure out where. Couple things to understand. There are 2 places that Git can execute code. First is locally or client side, and then secondly is server side. Typically, server side things are on self-hosted infrastructure only. So you're not going to just be able to randomly execute arbitrary scripts on github.com. Like that's not really a thing that anyone does. And on the client side, there are tons of places, so pre-commit or pre-push, et cetera, that you can do things. Pre-commit is the most common. And generally, you're going to find and replace text, no windows, type new lines. You're going to lint things there. And then on the pre-receive side, you can detect force pushes. You can block commits containing specific regular expressions, leaking secrets. You can block unsigned commits. However, again, on that client side, that's all endpoint controlled things. So just keep that in mind when you're going through an audit and trying to prove it. For infrastructure as code, I have one very, very strong opinion, and that is if you are using persistent infrastructure to meet any sort of control, don't ever use git checkout. Branches are pointers to commits, and explaining this has caused more gray hair than I care to realize. If you're doing this, try to clone with a depth of 1, meaning you're only cloning one specific tag. You're not getting the whole history of that. So you can say, hey, I only brought down this specific set of code. And there's a lot of ways to interact with Git remotes. So there's a lot of credentials and various controls that these can cause a problem with. So OAuth or GitHub apps, so these are designed to be bot or integration type controls. deploy keys, which you can give write permissions to. Personal access tokens or API tokens, again, user level controls, SSH account keys, oh, hey, commit signing keys, service accounts, single session JIT authentication. I'm going to pick on GitHub token because that's the ecosystem I know the best. But a lot of other things can generate secrets during this process. And again, the control that you're trying to map to, for me is AC2, which is account management and account lifecycle. You're trying to understand all of the different ways that this code could be pushed, or this code could be overwritten, or this code could be pulled or interacted with in any way. And that just starts to add up. There's been a lot written about commits and commit styles and pull request etiquette. I'm not going to go there. I am going to say, please provide a reasonably relaxed convention for your team that provides some structure and some room to mess up and change over time. The big thing I want to talk about is pull requests or merge requests. If you ever want to move platforms, so if you want to move between, say, GitHub, GitLab, Bitbucket, Azure DevOps, like all of those things have kind of their own take on that idea, and the data fidelity between them can change. So a lot of those bigger decisions, consider committing to your repository as an architecture decision record. So write a quick summary of why are we using NoSQL, or why are we using Kafka, or why are we using whatever other tech? What else was considered and why we went with it? And lastly, what can be done? Most folks settle on something that looks like this. If you want to add a little crypto, it looks like this. So you add a key server, and you're having a second factor for that endpoint. But OIDC is really, really promising. I'm going to say it's magic crypto. It's not. It is an open identity connection. So it is, you are who you say you are. It provides a central identity on a short-lived credential. But what if we could sign stuff with it too? And that's what SigStore does. It adds a certificate authority, and it adds a transparency log for verification. And all of the supply chains announcements that have come out of GitHub and a couple other places earlier this month and last month have all been built on SigStore. And then there's one other thing you can do, but what if we could sign our commits with it too? So this is what it looks like at work. I accidentally goofed up and have a verified commit there, but I did sign with SigStore, and unfortunately, GitHub, GitLab, et cetera, don't quite know how to interact with that yet. So it does show up as unverified. But if I go to that Recore transparency log, it will say, hey, Natalie had that for this time, and she signed that commit, and we're good. More importantly, you don't have to show up to every single argument you're invited to. And in an audit, this is the most important part. There's 800 ways to meet a lot of these controls. Write things down, decide where to centralize or not, and go from there. And also send everything to your SIEM, because that is what you need to be doing anyway. And yeah, audits are stressful. Your team is human. Your auditors are human too. It's all okay. I did not leave time for questions. I'm sorry. Oh, 2 minute and a half. Okay, questions.
I'll just shout mine out.
Okay. That is a loaded question, because I am not going to talk smack about Subversion. There's a lot of reasons that you would choose one over the other. And for me, it's more about everyone else is on Git, so I'm going to not, break that either. I will mention that the Subversion bridge, or that compatibility between Git and Subversion, is no longer supported by GitHub. So, yep. Yep, sorry. All right.